matter, just like the example in Oklahoma City, it doesn't matter if I go east first and then go south, or if I go south first and then go east. Doesn't matter. Okay? So let me give you a more kind of quantitative example. We've got, we'll make this a little bit, we'll say this is 30 degrees. Oops, didn't need to draw that yet. We've got this vector, it's 30 degrees, and the length of this is $2 miles. What's the x component of that vector? Now I'm asking you, what's the x component and what's the y component? If I walk from here to here, that's the same as if I walk from to here and then to here, or if I went from here and then here. So what's the x component and the y component of that travel? Or how would you figure it out? SOHCAHTOA, yeah. And this is a special SOHCAHTOA. What's special about it? It's what?
At right.
It's got a right angle. What else is special?
30 degrees.
It's got 30, 60, 90. So it's 30 here. So I need to make a triangle out of this. There's two different triangles I can draw. Which way do you want to go first? Right or up? Doesn't matter, right? Doesn't. I'm only going to do it this way. So I'm going to leave. So I've got two vectors here. Which way are they pointing? I've got an x vector. Which way is it pointing? Yeah. Which way is this one pointing? Just like when we added them, this one here, this is the resultant one. It's this one plus this one is equal to this one. The hypotenuse is the resultant one when you're breaking them down backwards. So what's the length of this one here? 1 mile. That's that 3069, that shortcut. 1, 2, square root 3. What's this one? Square root 3. 127 3 miles or something like that. Okay. So that 2 miles at 30 degrees north of east is the same as walking 1 mile north and square root 3 miles east. We did the shortcut for 30, so I didn't have to pull out the calculator. But we can do that for any angle, right? So we could take a similar approach up here. We're going to have to break this into an x component and a y component. Yeah, it's the same thing. We can draw the triangle on either side. We can draw a triangle coming down like this, or we can draw the triangle coming down here, because it doesn't really matter. In this case, it's not a path, it's force. But it doesn't matter where you draw it on either side. It's the same thing. You've got a force pulling up, right? And which other way is the force pulling? They're pulling out, opposite each other, right? Okay, so what we talked about last time is kind of a way to simplify this problem a little bit. Is first thing I'm going to go ahead and write 980 newtons there, and I'm going to simplify it just by the basis of symmetry. We've got this. These are both 45 degrees. Since symmetry, we know that each of these are holding up half the load here, right? So I'm just going to kind of ignore this part of the problem. So we know that this wire here is elevating half of that 980 Newton load. So what can we say about the y component of the force on this one? The y component. It's got to be 490. So where do we draw that 9? How do we draw this up here to kind of illustrate it? 490 north. We can draw it like this. We could draw it on the inside too, but it's a little bit crowded. So we know that component, and there's also a component like this, because this wire is pulling